did a biomedical engineering 3-year qualification prior to that. He is presenting work that relates to his final year project. He's currently working full-time and studying part-time. So we look forward to your work. You have 15 minutes. Thank you.
Good morning, I'm Joe Gandia, and today I'll be showcasing my low-cost hand gesture recognition system, which I designed with Timothy McBride and Prof. Nixon. I'll start off just by showing a quick video of the system. I'll first give a brief background of the hand gesture recognition problem and the design criteria that we use for this project. I'll then present the system design and implementation, as well as some test results, and I'll finally give some recommendations for future work. Prior attempts to do hand gesture recognition involved looking at specific points of interest in the hand, such as convex lines, or using a glove of particular prominent colors that stands out. The challenge with hand gesture recognition is that it usually requires some special equipment, and the end system usually just has a limited interaction between the human and the computer. For this project, the design criteria that we settled on was that the system should be able to recognize and classify specific hand gestures and then control a device in real time. Our main constraint was that the system should be as low cost as possible, and in this regard, run on a standard laptop. Finally, the assumption that we made is that only one user would use the system at a time, in a distance of between 1 and 2 meters, and that it will be operated in a plain and uncluttered background. The hand gesture recognition system that we designed is able to identify 6 dynamic gestures, 19 static gestures in real time with a delay of between 50 and 500 milliseconds, using only a webcam and CPU and not the laptop GPU. The system was designed both in MATLAB and used the MS-DOS framework to interact with the operating system. The final interface is made up of 2 phases, the calibration and implementation phase. In the calibration phase, the user must perform certain gestures to train the model. This must be performed multiple times in different environments, but each time that the model is trained, it learns a little bit more, and eventually the model will not have to be trained for future use. The first step is mimic data acquisition. In this step, the user is required to mimic a model on screen and perform the gestures as the model does. There are 19 of them, and it takes between 30 and 60 seconds to complete. This thing also includes a null gesture to compare to all the others. The images are then processed to prepare them for training. This is done by first resizing the images to 100 by 100 pixels, splitting it into left and right, flipping the right side, and then augmenting the data. Augmentation is done by randomly shifting or scaling the image, and the purpose of it is to account for variability in natural gesture performance. All of this augmented data is then passed to the CNN to train it to identify the 19 static gestures that I stated before. The CNN is trained on that augmented data, and if you want more specifications for the model, please see my paper. During training, you will see this plot which depicts the accuracy achieved for each iteration of training for both the training and validation data sets. As you can see here, the accuracy improves over time. Similarly, the loss function conversely decreases over time until an optimal solution is reached. The results of the training is then shown in the graphical user interface. We see here a confusion matrix which plots on the y-axis the gesture that was actually performed, against the gesture that was predicted by the system. In some cases, the system may predict the same output gesture for different images, and this can be due to the user not doing the mimic stage properly, and that would require recalibration. But recalibration will also be needed just due to the nature of the system not reaching a local optimum solution. Reaching a local optimum solution and not a global minimum. After the calibration phase, the implementation phase is done. This is when the user actually uses the system to control their computer. The image processing stage is similar to before, where the images are resized, split, flipped, but no data augmentation is done. Those images are then pushed directly into the CNN in sequence. And then the images, the user's pose is then classified by the CNN. For this project, I came up with a novel way of detecting where the user's hands should be, or where user's hands are. And I call this the virtual merge 3D grid space. The purpose of this is to, by splitting the image up into two parts, you end up training the model with a smaller image which reduces the training time, but also creates a better model because there are slight differences between the hand and the left. This method also allows you to do two-handed gestures instead of the one-handed gestures that I had in the original version. So after the gestures have been identified, we then have to after the pose has been identified, we then need to identify the gesture that was performed. This is done by detecting the sequence of poses that were performed. And in order to avoid false positives, we use a left select, right to force method. So what this means is that your left hand would select the type of setting or that you wanted to change, and then your right hand would then change that setting accordingly. So if you want to change the volume, it go up. If you want to reduce it, it go down, and so forth. Also, to try and optimize the detection of poses, we instead of opting for a regularly spaced 3D space, I actually used the golden ratio to split the space up into the different segments based on where the hands naturally occur. Especially for, and the whole point in this, the point of this was to limit the amount of overlap between different regions and avoid false positives as well. Finally, after the gesture has been detected, we want to actually perform some sort of operation on the computer. And this is done by, again in MATLAB, which interfaces with the MS-DOS framework and allows you to control keyboard, mouse, and other settings of the computer. In our research, we found that controlling the mouse is not a viable use for the system because the precision required to control the mouse is not provided by the model. So this is just a few examples of the type of gestures that the user can perform and the corresponding settings of control that they can effect. So you can change the volume, like I said before, brightness, which is similar to volume except your left hand is a little bit closer in. You can scroll. You can also press the arrow button and turn your monitor off just by waving goodbye, and Alt tab just by pressing it. For this, in our research, we looked at the different activation functions at each layer, and with this example image, those were the activations that were fired. And at the second layer, we actually found a kernel that was performing skin extraction apparently, and this is one of the reasons why we did not include skin extraction in the final model, because the CNN was basically doing it for them. Finally, just for future work, we would like to improve the interface with the computer because there was a bit of lag with the MS-DOS framework, and we would like to generalize the system so that the user would not have to train it every single time, but in order to do that, it would require a larger data set. Finally, we would like to train an RNN on the CNN classification sequence, and this will allow the user to define their own gestures instead of the predefined gestures which we have already In conclusion, the hand gesture recognition is a challenging problem, and prior attempts have had limited success. The HDR HCI system that we've proposed uses user calibration and stores the user's data locally. It uses a virtual mirrored 3D grid space, which is segmented by the golden ratio, and a left select, right enforce input method just to avoid false positives. The CNN is trained on each half of the image and controls the computer by means of the MATLAB image class interface. However, the performance was impeded by this interface. Thank you very much.
Excellent. Thank you. Open it to the floor for questions, comments, observations. I'm sure there must be some. There we go.
Which CNN architecture did you use?
So I just used a normal, it was basically, I'll show you, if I speak to you afterwards, I'll show you a better representation of it.
Okay. Did you have to tweak some parameters?
Yeah, I had to tweak the number of layers obviously, and then the number of nodes between each layer. I actually found that increasing the number of nodes between each layer provided a better output. But this was only after I switched over from using the full image to using the half image. Because when you do that, your left hand, then once you cut it and flip it across, it becomes basically like your right hand. So that allowed me to increase the depth a little bit more and increase the width a little bit more to get that out.
That was quite an interesting presentation. But my question is, if my two hands are cut, is your system able to tell with my face I do like this, right? And because
Actually,
let's assume that my two hands are cut, how do I control it?
Yeah, you are right. So this system, it isn't actually detecting like the specific shape of the hand like other systems that work. It's really detecting like the skin color, the position, and everything. So sometimes, like one of the assumptions that we made was that it would work in a clear background, because sometimes if someone just comes and sticks their face in one of the parts there, it detects it as a hand in that position. The fact is we're only using a very small network. It can't really determine the difference between a head and a hand. It's really looking for the color and the position.
Can I ask the question I asked earlier? What would be the next thing if you had the luxury of more time? What would you do with the system? Is it worth pursuing, or is it?
I think it definitely is worth pursuing. However, having that low cost constraint is, it's a bit of a trade-off. If I could remove that low cost constraint and maybe get it to run on a GPU, what I would really like to do is run it using a 3D convolutional neural network, because that way you can get temporal information as well and not just have to look at the sequence. One of the recommendations I made for future work is that I could use an RNN on the CNN sequence, but that would be completely unnecessary if I had been using the 3D. But that obviously
Excellent. Thank you for your presentation.